Good morning, ladies and gentlemen. My name is Nicholas Bramhall, and this is the Lab 3 Post-Lab Reports. Let's get into this. So, introduction. The point of this lab was to explore the basic functionality of circuits and to prove loop and node rule. Ultimately, we found that the total change in voltage across the circuit to be about 0.2 volts, and it took around 11 seconds for a 1 ohm resistant bulb to go out and 33 seconds for a 4 ohm resistant bulb to go out. All right, so these are the formulas that we're going to be using in this. We've got the good old Kirchhoff's current law, which is basically just that, also known as node law, which means that at any point the current going in has to equal the current going out. And then voltage law is that the total sum of all of the change in voltage across the entire circuit should be zero. And then, of course, there's Ohm's law, which is just voltage equals current times resistance, and you can have it in many different ways, as shown on the right. All right, let's go forward. So the first part of the experiment was when circuits are in series. So we have 2 amp meters, 2 resistors, and 2 batteries, and they're all in a closed loop. The circuit is the system. We don't care about anything else. Everything else is surroundings. And what we found, well, what we predicted was that the current would, of course, be 20 milliamps, assuming that there was a resistance of 1 on the outside. And the reality is that there was a current of 18 milliamps, which shows that there's a little bit of resistance in the wire that we are neglecting to account for in this experiment. And when we reverse the direction of reading the current with the ammeter, we found that the sign's reversed. Now with the voltmeter, we found that there was around, when we replaced one of the ammeters, with a voltmeter, we found that right there was around 2.8 to 2.9 volts, while the ammeter dropped drastically down to 3 milliamps, and it's because the voltmeter has a much higher resistance, which of course drops the current. So the conclusion for the series was that the total voltage was around 3 volts. The 14 ohm resistor change in voltages was around negative 0.9 volts, and the 100 ohm resistor had around a change in voltage of negative 1.85. The total delta V, or change in voltage, was around negative 0.25, and as you can see here on the right, we should be expecting 0, but the fact that there's still some change in voltage hints at the fact that there is some voltage dropping off due to just normal resistance in the wire, or the amp meters interfering or something. It could be any one of those two things. So yeah. Now in the next part, when we have it in parallel, we had 2 voltmeters in parallel. The amp meter read was around 17 milliamps, so about the same. And the voltmeter has a very high resistance, so most of the current actually went through the 100 ohm resistor rather than the voltmeter, which makes sense because it would take the path of least resistance. So ultimately, it didn't really change the circuit that much. Now, when an amp meter was in parallel instead of a voltmeter, we had it jumped to 60 milliamps, which shows that the low resistance of the ammeter, showing that the current would much rather go through the ammeter rather than the resistor, which is why the ammeter is so high. And so using this data, we can calculate that the actual resistance of each part was, instead of the 100 ohms, we calculated to be 102.77. So it's about equal, which means that there's probably some low rounding errors for the 2.77 ohms. And same thing here with the 47, as it's calculated to be 50. So we're picking up an extra 3 ohms somewhere from rounding errors. And then, as we said earlier, that we're neglecting the resistance in wire and voltmeter, and so we're just assuming them to be 0. So the deltas of part 3, the RC circuit. And so it's about the same initial conditions, same system and surroundings too, of same circuit, same surroundings, same, yeah. Batteries, 3 volts total still, 2 bulbs, one is 1 ohm and one is 4 ohms, and then we have a 1 farad capacitor. And so in series, we charge the batteries, then we disconnect the batteries to discharge into the light bulb. So in here, we saw that the 1 ohm battery dimmed slowly and then went out quickly for charging, and then it dimmed faster and then went out also about just as quick when discharging. And then 4 ohm, it dimmed slower and it embered for a long time when it was charging, and it dimmed faster than when it was slowing, than when it was charging, and it embered for a very long time too. And we can see here the times below. So how long would it take to charge a capacitor of 0 resistance? theoretically, it should be instantaneous because there's no resistance, so all the current can directly shoot right into it. However, in real life, there's resistance in all forms of matter, such as the wire, battery, and capacitor itself. And so in testing, it took around 4.4 to 6 seconds. So for our final notes are that the assumptions we made was that the wire and ammeter have no resistance, as that would make calculations messy, and the batteries were fully charged and have no internal resistance, so that they were supplying the full 3 volts, and then possible sources of error was rounding errors when calculating and imprecise errors in measurements and setting up the connections. Thank you.